Hello everyone, this video is brought to you by the Atılım Üniversitesi OpenCourseWare project for the course Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and video lectures are prepared by Ümit Alkuş. In this video, we will solve one problem in Chapter 11. A uniform sphere rolls without slipping down an incline or angle theta, which is 16.3 degrees. A. Draw the free body diagram of the sphere. B. Find the linear acceleration of the center of mass. And the rotation inertia of the sphere is I equals 2 over 5 m times r squared. In part A, we draw the free body diagram of the sphere as follows. First, we represent the sphere as it is. The gravitational force acting on the object is a downward force with magnitude m times g, and it can be decomposed into the components parallel and perpendicular to the surface. Another force acting on the object is the normal force due to the surface. Finally, since the contact point does not move, then there is no kinetic friction, but there is a static friction. And it's an upward force along the incline. Because the sphere rolls down, angular acceleration is drawn like this. Consequently, the linear acceleration vector A is depicted like this. And that's all for the free body diagram of the sphere. In part B, we use the Newton's second law, which is F net equals m times A, to find A. In the x-axis, F net has the component as m times g times sine theta minus Fs, which is equal to m times A. And we call this equation as 1. In the y-axis, we have n minus m times g times cosine theta is equal to m times 0, since there is no motion in the y-axis. Therefore, n equals m times g times cosine theta. In order to find an expression for A, we find the torques on the object. The torque due to the gravitational force, that is tau mg, equals r times m times g times sine beta. According to the configuration, beta is 0. That is, the extension of the gravitational force passes through the rotational axis, that is of. The torque on the sphere due to the normal force is tau n equals r times n times sine gamma, which is equal to 0, because gamma is 0. In other words, the extension of the normal force passes through the rotation axis of. And the torque on the object due to the friction is found to be tau Fs equals r times Fs times sine x, where x is the angle between Fs and r, which is 90 degrees. Then we obtain tau Fs equals r times Fs. Finally, net torque on the object is tau net equals r times Fs. We say that only the static frictional force causes a net torque. Here, we use the Newton's second law for the rotational motion, that is, net torque equals I times alpha, which is equal to r times Fs. We use the expression for Fs by the equation 1 as Fs equals m times g times sine theta minus A. And because alpha equals A over r and I equals 2 over 5 times m times r squared, the expression for net torque is written to be 2 over 5 times m times r squared times a over r equals r times m times g times sine theta minus a. And after some cancellations, we obtain 2 over 5 times a equals g times sine theta minus a. From this equation, we obtain an expression for a as 5 over 7 times g times sine theta. Now, we substitute the numerical values into this equation. Finally, we find the linear acceleration of the center of mass as approximately 1.96 meters per second squared. Okay, this is the end of the discussion of this problem. Thank you for your attention and see you in the next video.